Okay, it started. Good afternoon, guys. Welcome to the class. And I will continue the class with the next problem. See, if you look at the figure of the problem, see, this is the plane of the weld. The plane of the weld is running perpendicular to the paper or the screen. Okay. And when it comes to the load is going to be in a different plane. So this is called type 2 connection. So whatever problems we have solved on brackets until now were type 1 connections, and what problems we are going to start from now on until the end of this chapter, it is going to be type 2 connections. So in case of type 1 connection, the weld was subjected to shear, direct shear and torsional shear, both. Okay, that is the reason why we use the formula T by IP equal to Fs by R equal to C theta by L. That was the torsion formula we used. But in type 2 connections, wherein the weld and the load are on two different planes, then we have to make use of the bending equation. So this is the bending equation. That is E by R equal to M by I equal to F by Y. So E by R, of course, we don't use it. So I'm going to maintain this, and we are going to use this equation to solve the problem. Okay, and that is M by I equal to F by Y, and M is this much. I by Y max, that is the distance of the farthest fiber from the neutral axis. So I by Y max is the section modulus, so that is Z. So Z is given by BD square by 6. How did we get BD square by 6? Where I equal to BDQ by 12 for a rectangle section, and the distance of the farthest fiber from the neutral axis is D by 2. So when you simplify it, we are going to get this value is called the section modulus. Next, coming to the problem. So a bracket plate is subjected to a load of 100 kilonewton at an eccentricity of 120 millimeter and is connected to the face of a steel stanchion by fillet weld. So this is a bracket plate. Okay, this is subjected to a service load of 100 kilonewton. What is the eccentricity? 120 millimeter. So, and this is connected to the face of a steel stanchion. Steel stanchion is nothing but a steel I section. And this is the flange to which this bracket plate is connected through the weld. And the weld is provided on two sides. One is on this side and the other weld is on the other side. Okay. So going further, stanchion by fillet weld on both sides of the plate. Of course, we are providing weld on this side as well as on the other side of the bracket plate. So determine. So we have three parts in this problem. Number one is the size of fillet weld. So we need to find out what is the size of the fillet weld to take care of this load. Next one is, if 8 millimeter fillet weld is used, determine the depth of bracket. See, on what basis we are going to fix the depth of the bracket? We are going to fix the depth of the bracket based on the length of the weld we need. If we need, say, 400 millimeter weld, then we have to have a bracket plate of depth 400 millimeter. In this case, what is the bracket plate depth? Bracket plate depth, that is 300 millimeter. Okay, so the second part of the problem is, if 8 millimeter fillet weld is used, if you are using 8 millimeter fillet weld, so what is the depth of the bracket we need? Okay, that is another part of the problem. And the third part of the problem is, if 8 millimeter fillet weld is used with a bracket of 250 millimeter depth, okay, calculate the resulting stress in the weld. So what is the resulting stress in the weld? That means, what is the stress in the weld which is located at the farthest distance from the neutral axis? because that is a weld that is going to be stressed to the maximum. So coming to this problem, solution. The load to which the bracket plate is subjected to is P, that is equal to 100 kilonewton. That is given, that is the service load, as I said before. But we have to consider the design load. So design load, factor load, or ultimate load. So that is PU, that is equal to 1.5 times, that is the load factor, multiplied by service load. We got PU equal to 150 kilonewton. So eccentricity E is given, that is 120 millimeter. So I have written a note here. So the note says here the depth of bracket given is 300 millimeter. In case of design of weld, where we are required to calculate the depth of the weld along with the weld size, we need to assume certain weld size, then find out the depth of the weld required. So the depth of the weld is same as the depth of the bracket plate. What it means is, if you are given a problem like this, if you are not given this weld depth, sorry, bracket depth, and also if you don't know what is the weld size, then in this case we have two unknowns. One is the depth of the bracket and the other is the weld size. So in this case, to solve for two unknowns, we have to assume one of those two things. So the one thing we are going to assume is the weld size. We are going to assume certain weld size. That way we'll end up with the depth of the bracket as the unknown. Then we can find out what is the depth of the bracket required to accommodate that size of the weld. Okay, that's what the meaning of the note is. So we'll come to the first part of the problem, that is to calculate the size of the fillet weld. So it says the size of fillet weld, find out. So for this load of PU 150 kilonewton. So when you look from this side, as I said, we have two lines of weld. One is on this side, the other is on the other side. So this is the way we are going to see when we are looking from this side. In between these two welds, we have bracket plate. Okay, so bracket plate thickness doesn't matter for us. Okay, when we consider, say for example, this weld, which is rectangular, where TT equal to thickness of the throat and D is 300 millimeter. Okay, and this is the neutral axis. So because this is subjected to eccentric load and the connection is type 2, the weld is subjected to direct shear, okay, as a result of this, and also the moment which causes tension in the weld. In the type 1 connection, both F1 and F2 were shear stresses. In this case, one is shear stress and the other is the normal stress. So if you consider the bottom one, it is compression. If you consider the top, that is anything above the neutral axis, the weld is going to be subjected to tension. So we have tension and shear. So whatever we name, we give, whether tension, compression, shear, or etc. Finally, we'll end up dealing with two forces. Okay, one is the horizontal force pulling the weld in this way, and the other is the shear force or shear stress acting downwards like this. Okay, so coming to this, as I said, we are going to make use of this formula. We'll find out what is F1 value, that is the direct shear stress F1. Okay, so F1 value is given by PU divided by total throat area of the weld. So if S is the size of the weld, TT is the throat thickness. Here we need to find out what is the size of the weld in the first problem. Is it not? Okay, we are going to call that as S and TT. So we'll find out F1 first. F1 is PU divided by throat area of the weld. What is PU? 150 multiplied by 1000 to convert the value into Newton. Throat area of the weld is given by TT multiplied by 300. TT multiplied by 300. Multiplied by 2 because we have 2 welds. So finally we got this value equal to 250 by TT. Okay. And see, as far as F1 is concerned, it is uniform throughout the length of the weld. Each unit area of the weld is going to be subjected to a uniform shear stress of this value. But when it comes to normal tensile stress or bending, tensile stress here and compression in this side. This is the neutral axis. So this is the weld which is going to be subjected to a maximum tensile stress. As we move towards the neutral axis, the normal stress is going to be reducing. At the neutral axis, it is going to be 0. Similarly, on this side, 0. As we go down, compression increases, and the extreme side of the weld on the bottom is going to be subjected to maximum compressive force. As of now, we don't worry about this. We are going to solve for this problem, and that is going to be equally applicable for this side. Okay. So as I said, the extreme weld is going to be subjected to maximum tension, which we are going to find out how much it is. So that is F2 value. That is F2 value is given by M by Z. So what is M by Z? Look here. F equal to M by Z. Okay. So coming to M, it is the design load multiplied by the eccentricity. So these two things are known. Z is the section modulus, BD square by 6. So by substituting the values, 6 multiplied by PU is 150 multiplied by 1000 Newton, multiplied by the eccentricity is 120 millimeter. And as far as B is concerned, it is going to be 2 times the thickness of the throat. There is one and there is the other. So 2 times TT is the thickness of the throat, total thickness of the throat, multiplied by D square. So that is the depth of the weld. So we got F2. So if I consider an unit area at the extreme fiber of the weld, see, this is where I have shown. This is the neutral axis, XX. So this is half the depth of the weld, 300 by 2, that is equal to 150 millimeter. And that unit area of the weld is going to be subjected to a normal stress of F2, normal force, because when I say unit area, it is normal force, and a shear force of F1. So if I consider the resultant of these two forces, so F is the resultant force on that unit area. Okay, find out what is F. So we know F1 and we know F2, substitute the values. We got the final value of F equal to 650 by TT. So this is the stress to which the extreme weld is subjected to. Or this is the force to which unit area of the extreme weld is subjected to. Okay. Then what is the design strength of the weld? Design strength of the weld FWD equal to FU by root 3 multiplied by 1 by gamma MW. This is the formula we have from here. Okay. So find out what is FWD. So here we are assuming that the welding is being done at the workshop itself. Okay. So when it is done at the workshop, as per table 5 on page 30, this is 1.25. So find out what is FWD. Once we have this FWD, which is the design strength of the weld, so equate that to the resulting stress of the weld at the extreme fiber. Okay. So by equating these two values or these two equations, we got the thickness of the throat equal to 3.43 millimeter. But we know the thickness of the throat equal to 0.70 times S, where S is the size of the weld. So TT is 3.43. We got the value of 4.9 meter. Therefore, we shall provide a weld of size S equal to 6 millimeter. If you want, you can provide 5 millimeter weld. That is good enough. but I have provided 6 millimeter weld. So that should be able to take care of the design load coming on the bracket. Is it clear to you? So next, part 2 of the problem will go. What does it say? If you look here, if 8 millimeter fillet weld is used, determine the depth of bracket required. So in the first part, depth was given, we had to find out what was the size of the weld required. But in the second case, weld size is given, we need to find out what is the depth of the bracket required. Same formula, same steps, absolutely there is no change. Look here, here D is the unknown. So if 8 mm fillet weld is used, determine the depth of the bracket. So we say let D be the depth of the fillet weld required. Okay. So that is equal to the depth of the bracket itself. So throat thickness is equal to TT equal to Ks, where K equal to 0.70 multiplied by 8. 5.6 millimeter is the throat thickness. Okay. Then the depth of the bracket or the depth of the weld here, yeah, both of them are one and the same. Okay, is given by D equal to 6m divided by 2t multiplied by FWD1. It is not FWD. How did we get this? If you look at this formula, again, bending formula. So look here, we got this value. So what is D? Square root of this much. D is equal to square root of 6m divided by 2t F. So in this case, we are going to substitute not F, FW1. So what is FW1? We are going to take FW1 equal to 0.80 times FWD. Why we take the reduced value of FW1, reduced value of FWD? To get the higher value of D. If you directly substitute FWD here, you get some depth. Okay, instead of directly substituting FWD, you take 0.8 times of that. So you will have some value at the denominator. D value will be increasing. Why we do that? Because extreme weld is going to be subjected to direct shear and a tensile force. Look here, like this. So when we are determining the depth of the weld, we are determining based on only this F2 value. Okay, but we are not considering this. This also, contributes to the stress. So to account for this, we need to give higher depth more than what is required for just F2 alone. Is it clear to you? So if you come down again, so again this depth is based on this F. This F is nothing but F2 value, but extreme weld is going to be subjected to not only F2, it is going to be subjected to F1 as well. So even to take care of that part as well, we are going to reduce this FWD value, which is equal to 0.80 FWD, that is equal to FD1, and we are going to substitute lower value of FWD. Okay, that way we are going to get higher value of D. Okay, so that is going to take care of both F1 and F2 stresses. See here, a reduced value of 80% in the above equation should be used to account for the effect of direct shear stress. That is F1 value. Okay, so here, if you look here, 151.5 FWD1 value. So substitute all the values in this equation. Okay, we get the value of D equal to 252.3 millimeter. Okay, so therefore let us adopt a bracket plate of depth 280 millimeter. Is it clear to you? Next, once we have provided 280 millimeter, but we are not sure the depth is adequate because we have taken the reduced value. That's fine. We have taken only 0.8 times. Why not 0.7 times? Why not 0.6 times? Why not 0.9 times of FWD value? So this is based on experience, but just because it is based on experience, it does not mean that this is going to work. Okay. So after taking this, after finding this value, we will go back and check what is the stress developed in the extreme weld. If that stress developed in the extreme weld is within the limit of FWD, then whatever depth we have provided is adequate. Or else we have to go back and we have to increase the depth further beyond 280 millimeter. Okay. Now we'll check our design whether it is okay or not. For that, let us find out what is the stress at the extreme weld. So to calculate the stress due to design load, direct shear stress, first case, so that is Pu divided by 2 TTD. Okay, that is F1 value, 47.83, which was not considered above while finding out the depth. So, okay, next comes F2. Again, this equation we have, find out F2 value, 123. So, find out what is the resulting stress in the extreme weld. That is equal to F square root of F1 square plus F2 square. That is equal to 132 Newton per millimeter square. Okay. So once we have this value, find out what is the design strength of the weld, which is FWD. Okay, by taking, say, sharp weld. So this is the value, design strength. This is the actual stress developed at the extreme weld due to the design load or factored load. So F is less than FWD. That is, the stress developed at the extreme weld due to the external design load is less than the design strength of the weld. Therefore, whatever the depth of bracket plate we have provided is good enough. That is adequate. Is it clear to you? So third case, it says if 8 millimeter fillet weld is used with a bracket of 250 millimeter depth, calculate the resulting stress. This problem is direct. They have given the load, okay, that is whatever the load given multiplied by 1.5, that is 150 kilonewton. They have given the weld size. They have given the depth of the bracket. Find out what is the stress, resulting stress developed at the extreme weld. So we can find out that. It is a straightforward formula and straightforward problem. So thickness of the throat is given by 0.7 times 8. 8 is the weld size. That is equal to 5.6 millimeter. Now, what is the direct shear stress in the weld? F1 equal to Pu by 2 TTD. Okay. So 5.6, D is 250 millimeter. Where it is 250, that is given in the problem. Okay. It says with a bracket of 250 millimeter. So bracket plate depth is going to be 250 millimeter, and we are going to provide the weld over the entire length. So bracket plate depth equal to the depth of the weld. So finally we got F1 value equal to 53.57 Newton per millimeter square. Then normal bending stress, F2 value, which acts in this direction, that is perpendicular to the plane. So that is M equal to F2Z. So F2 equal to 6 PE 2 TT D square. Okay. So F2 equal to 6 PE, substitute the values. We got F2 equal to this much, 154.29. So then what is the resultant stress F? So that is bending stress is acting like this. Shear stress is acting like this. So both of them are at 90-degree apart. Okay, so the resultant will be acting somewhere along this. So because this is a rectangle, normal stress, sorry, bending normal stress and the shear stress complete the rectangle, diagonal represents the resultant. So that is given by square root of F1 square plus F2 square. So that is equal to 163.32 Newton per millimeter square. That is the resulting stress due to the design load. Therefore, what is the resulting stress due to service load? What is the service load we are applying? Only 100 kilonewton, is it not? So, whatever the value we calculated, for this value equal to 150, this should be PU, okay, not P. So, this should be for 150, okay. For service load, divide this value by 1.5. So, 108.88 Newton per millimeter square. That is the actual stress the extreme weld is going to be experiencing as a result of 100 kilonewton service load. That is the actual service load to which maximum load to which the bracket is subjected to in reality or in service. Okay, so this is the stress. Next, coming back to this, we dealt with 3 cases. So case 2, we can find out exactly the depth. See, I'm repeating case 2 by method in the second method. What is case 2? If you remember, if I go back, see here, case 2, if 8 mm fillet weld is used, determine the depth of the bracket. Okay, so depth of the bracket, I have taken FWD1 equal to 0.80 multiplied by FWD to account for the effect of F1. Is it not? So instead of doing this, can we directly find out what is D? Yes, of course you can do it. It is painful. Okay. However, I have done that. I'm going to show it to you. Okay. And I'm going to explain it. So it is better you stick to this method. That is by taking 0.80 multiplied by this value because this is easier. So another method I've shown is if 8 mm fillet weld is used, determine the depth of the bracket. I called this as D. It says this is a second method on how to calculate the depth of the weld. So weld size is equal to 8 millimeter. Throat thickness is 5.6 millimeter. So what is the direct shear stress F1? That is 150 multiplied by 1000 multiplied by the throat area. 5.6 is the throat thickness. Depth is the depth of the weld multiplied by 2 because we have 2 such welds. So whatever value we got is in terms of D. Similarly, normal bending stress F2. So PU is this one. We know the value of eccentricity. We know PU. So Ymax is the distance of the farthest fiber of the weld from the neutral axis. That is D by 2. Okay. So Ixx, that is the moment of inertia about the neutral axis, horizontal neutral axis. Again, we got this value in terms of D cube. So by substituting the values in the above equation, we got F2 equal to this much. See, look here, F1 is this, F2 is in terms of D square. Then we have this formula, resulting stress equal to F, that is equal to square root of F1 square plus F2 square. Okay, so substitute the values, call that as equation 2. Okay, now find out what is the design strength of the weld. Okay, design strength of the weld is FWD, that is equal to 189.37 Newton per millimeter square. Okay, so equate these two, equation 2 with equation 3. So we get this equation, square it. Say, look here, we got the equation, fourth degree equation, d to the power of 4. This is going to be painful. So how to solve this? So we are going to solve this through the process of iteration. Okay. So initially what we do, we are going to assume d equal to 0, depth equal to 0. Of course, it cannot be 0, but somehow we have to start somewhere. So when you substitute in the process of iteration, when you substitute d equal to 0, you have to substitute the value in place of d except it has the highest power. Okay. So here substitute 0. This value remains as it is. Find out what is d, that is equal to 231 millimeter. Now we got the first approximation of the depth of the weld, which is 231 millimeter. Okay. And sorry, 226 millimeter. 226 millimeter. So again, go back to this equation. Now instead of substituting 0 in this equation, go back to this equation. Now this time, instead of substituting d equal to 0, substitute the first approximation, which is 226 millimeter in this equation. So next iteration value d equal to 231 millimeter. See, initially d0 we assume. We got 226 in the second iteration. Sorry, in the first iteration. So in the second iteration, we got 231. Go to the third iteration. In this case, take d equal to 231 millimeter and substitute 231 here, except this. Okay, we got 231.26. See, this is what the iteration is. So start with some initial value. Okay, as you progress, the value of d or the value of the unknown converges towards the true value. See, 0 to 230, 226, 226 to 231, next 231 to 2.6. If you go and do one more iteration, you may get 231.28 or 27. Okay, instead of doing all those things, just stop at this point. This is enough. This accuracy is good enough for us. Okay, so once you have this, so let us provide, instead of providing 231.26 millimeter, we will provide 240 millimeter weld. So that is the depth of the bracket plate. Now we can go back and we can check what is the actual stress developed. So once we have the value of d, 240 millimeter, so come here, substitute the value of d, 240 millimeter here in this equation. So we got 176.46 Newton per millimeter square. So which is less than FWD value. So our design is safe. Okay. So we can find out the depth of the weld or depth of the bracket plate in two ways. One is the easiest way. This one is little bit longer. You are supposed to know how to do the iteration part. So of course, iteration is not so difficult. Okay. So this way, if you provide exactly 231.26 or 231.33 of the weld and find out what is F value, you are going to get this value almost equal to this. Because we increased the depth 231.26 to 240 millimeter, this value of F is equal to 176.46 Newton per millimeter square, which is less than, and of course it will be less than 189.37 Newton per millimeter square. Is it clear to you guys? So with this, so I'm going to complete this problem. So in this module, I'm left with another two problems. Okay, so which I'm going to complete tomorrow. I'm going to complete tomorrow. Even tomorrow's session is not going to be that long. Okay, once that is over, So this syllabus is, sorry, this module is complete, and the next module is going to be the design of compression member. Okay. So again, guys, thank you. Be safe, and we will meet again tomorrow at the same time. Take care. Bye.
Bye, sir.
Bye.